Hello and welcome back to another LeetCode problem. Today we're looking at LeetCode 1518, water bottles. It's an easy problem. I have attempted this problem before. We're going to do it interview style today, where we follow our systematic process of understanding the problem, asking for the constraints, looking at the examples, coming up with our own solution, as well as its runtime and space complexity before we write the first line of code. And then we're going to implement our code explaining what we're doing and maybe iterate on it to optimize it. So let's get into it. So here we are dealing with the water bottles problem. We are giving num bottles of water bottles that are initially full of water. You can exchange empty water bottles from the market with one full water bottle. So we get refills. The operation of drinking a full water bottle turns it into an empty bottle, obviously. Okay. So we're given two integers, the number of bottles and the exchange rate, num exchange. And we should return the maximum number of water bottles we can drink. Okay, and I'm guessing there is going to be a closed form solution as well for this, as well as maybe one that just iterates over it. And now for the constraints, I would want to know what are the smallest values that these two variables can assume, and maybe if any of them have an upper bound. So let's look what LeetCode tells us. Okay, we have at least one water bottle, and if we want to replace a water bottle that is empty with a new one, we need at least two empty water bottles to replace them for one full one. All right. Now let's look at the examples. So here we have number of bottles is 9 and the exchange rate is 3:1. So we get one full bottle for 3 empty bottles. So we have 9, we drink 9 water bottles, we get 9 empty ones. Then we exchange them. So, and we can exchange 3 water bottles for 1 full, so we get 3 full. Now we can drink them as well. So we now have 9, 10, 11, 12 bottles that we drank. We can perform another exchange because we still have enough empty bottles. And we get 1 bottle back that we drink and then becomes empty. So the result would be 12 plus 1, which is 13. That's the total number of water bottles we get to drink. All right, so, and we can already see, the process. What I just went through, we could implement it directly as code. That is the reason why you go through these examples, because it gives you a recipe for a naive implementation. Okay, example 2. Okay, here we have 15 bottles to start with, and our exchange rate is 4:1. So now 15 is not divisible by 4, like we had before, where 9 was divisible by 3. So now we can drink all initial bottles. We get 15 empty bottles, but we can only exchange 12 of them for 3 new full bottles. Now this gives us 4 new empty bottles, and now we have 6 empty bottles in total. So we can do actually one more exchange, and that leaves us with 3 empty bottles. So in total, the result would be 15 plus 3 plus 1, which is 19. Okay, understood. Okay, so in terms of approach, so if we implemented just this iterative approach where we drink and then we get our refill and we continue to drink the water bottles as long as we have as long as we have any water bottles that are not empty. And we go to the market as long as we have more empty water bottles or as many empty water bottles as the exchange rate tells us. So I don't think we need to store anything besides the result and update maybe our number of bottles variable. So that would be constant space. And in terms of runtime, it's not linear, right, in the number of bottles, because it is guaranteed that the exchange rate is at least 2:1, right? So it's so at every step we are halving the number of bottles, roughly halving them. So, and that's exactly the inverse of an exponential growth, right? We have like a logarithmic runtime, because of every step, if you divide something, if you were to divide 2 to the n Well, it's basically, what's the best way to put it? If you have a number k and you wanted to count how many bits that have, you wouldn't have to iterate from 0 to k. You would have to iterate from the first bit to the last bit. And that's log k bits in a number to store a value of k, roughly. So this would be O of n, well, no, just log n runtime and O of 1 space. And yeah, let's just implement the iterative approach. In an interview, I would just ask the interviewer, is it okay if I implement this now? Yeah, of course, of course. And it's always good to have a quick win. Try to implement the easiest solution first. That gives you some points. It warms you up for the interview. And you have more to talk about when you talk about optimization. If you just one-shot like the perfect solution, well, nobody got to see your reasoning for why you did that. Or nobody got to see what trade-offs you made, etc. pp. And sometimes a faster solution means you're going to have to increase the space complexity as well. So sometimes there really is a trade-off. Runtime isn't everything. So yeah, but I'm rambling now. So result. So that's what we know initially we can drink, num bottles of water. And now we need to go into the loop. And I would actually that makes a lot of sense, right? We separate the initial number of full bottle from the loop where we get our refill. So yes, and so now what we do is, well, we have to keep track of how many empty bottles we have. And that's just going to be number of bottles, right? And now we do a loop while the number of empty bottles is larger or equal to, well, however many bottles we need to exchange for a full bottle. And then what we do here is we upgrade our result actually with something. And we have to now compute, okay, how many empty bottles do we have after the exchange? Well, so that's the part of the number of empty bottles that we will keep, right? And that part would be the num bottles modulo exchange. That's the rest of the division. But then we also get a number of empty bottles. And that is actually, well, we get a number of bottles back. That's the number of full bottles. And empty bottles is the rest. So remaining empty bottles and the new full bottles. So now we can increase our result by the number of full bottles. And then we have to increase our number of empty bottles because we just drank them. Yeah, and that's pretty much it, I believe. I think that's the entire thing. And yeah, let's just run this through the test cases. Oh, this is not going to work because we never, well, our num bottles, we're not changing it, right? We're just saying empty bottles. So here we have to put empty bottles in our condition. Oh, I keep making mistakes. So empty bottles is not used here. So we're dealing with empty bottles. That's what we need to put here. Two mistakes, two easy mistakes. That of course shouldn't happen in an interview, and would have been better if I went through it line by line, explained it after I implemented it. Okay, and that seems to work. Let's submit it. All right, cool. So that works. And we now have to look at, well, how can we optimize this? Well, let's try our best with a closed form. And the closed form would give us constant space and time. And how would that work? Well, I would argue that in the beginning, we still need our initial consumption of the number of bottles that are full. And we now need to come up with a formula of how to compute that. And the trick with that example, and I had to look that up myself because I couldn't find the solution. So I'm just going to present you basically the result and the reasoning. So if we have num bottles, empty bottles to start with, right? And if we just take that number and do an integer division by num exchange, that tells us how many bottles we're going to get back. That's exactly what we did down here. But we could also say, well, in reality, for every num exchange bottles, we're getting 1 full bottle back. And that is equivalent to just dividing it by num exchange minus 1. So we bake in the returning by 1. So actually we are reducing, at every exchange at the market, we are reducing the number of empty bottles, not by num exchange, but by num exchange minus 1. So that's why we have to do this division, right? And now this is something that I at first did not understand, but there's another component to this. We cannot just divide num bottles by num exchange minus 1. That doesn't work. Because what will happen is, if you take this example here, you take num bottles, that is 9, and you divide it by 2, integer, that's 4, right? So 4 plus 9 is 13. That works out. This 9 plus this 4 is 13. That works out. But in the other case, where it's not an even division, when you have the number of bottles is 15, and so you have 15 plus 15 integer division by 3, right? 4 minus 1. So that would now be, well, what is 15 divided by 3 is 5. You would have 15 plus 5, which is not 19, it's 20. And so this will lead to an off by 1 error. And if you go through a couple of examples, you can actually see that, right? And yeah. Yes. And that is how that works. Now, depending on your interview form, you might be able to come up with this or not. If you're not able to come up with this on the spot on your own, like I did, you actually have to do the calculations, work through some examples, and then you'll see that you actually have to add the -1 to fix the error that you're getting in your examples. And yeah, and this can be time consuming, to be honest. Unless you really have a good explanation. Okay, we need to do -1 because blah, blah, blah. We already consumed n bottles here, so we cannot do the same here, etc., etc., etc. So yeah, so this is another approach. I just wanted to show you that. And I don't think you need to sweat it if you don't come up with that in an interview. You know, if you can already say there's probably a closed form and you would have to do X, Y, and Z to find that closed form, that is already giving additional signal that might be quite good. And oftentimes the interviewer won't stress you on implementing something that is tricky or where there's like a lot of effort for an off by 1 error or something. So yeah, but knowing these things and understanding them is useful in my opinion. Thanks for watching.